So let's now look at the case where we use a least squares fit of our data using a sinusoid. So if you recall, what we've just learned is that we can describe a function in terms of sinusoidal values, that is f of t equal a naught plus a1 cos omega naught t plus b1 sine omega naught t. And you can think of this as a least squared model. So y equals a naught plus a1 cos omega naught t plus b1 sine omega naught t plus some error term. You've seen this before in terms of polynomials, that is y equals a naught z naught plus a1 z1 plus a2 z2 all the way to zm am plus the error term. But here z1 is cos omega t, z2 is the sine function, and z0 in this instant is equal to 1. Alright, so we can rearrange this to have the sum of squares of the residual, that is the sum from I equals 1 to n data points of yi minus a0 plus a1 cos omega naught t plus b1 sine omega naught t. And that is all squared. So we can then take this into matrix form, just like we did for least squares of the polynomial case. That is n sum cos omega t, I'm just going to abbreviate it as c, sum sine omega t. Next set of equations would be sum of cos omega t, sum of cos squared, sum of cos multiplied by sine, sum of sine, sum of cos multiplied by sine, and sum of sine squared. Okay, this is a set of linear equations. Here's our coefficients. That all equals to sum of y cos omega t, sum of y sine omega t. Alright, so we could exploit some Gaussian elimination technique to solve these linear set of equations, but I'm going to show you an interesting concept that we're going to use, or a special case that we're going to use to try and simplify this matrix. So let's examine the special case when there are n observations at an equidistant spacing interval of delta t, and that means we have a total length of n minus 1, capital N, times delta t. Okay, so let's just clear this board and look at a graph before we carry on. So we know that our function is going to be some sinusoid. So I'm just going to draw it in red for one period. Okay, and we only have data points here at 0, so this is the sine, so this is pi over 2, and yeah, so we're looking at one period. We could also have a cos function because we're going to need that, so that's going to look something like this. Okay, and we have the data points at the same location. Alright, so if we do a sum of sine, that's our red line, omega t, over n, you should find that the total there is equal to 0. And let's look at this. If our amplitude here is 1, then this is minus 1. These intermediate points are 0, so if we sum that up, we'll get 0. And that is the same for the sum of cos omega t over n. It's also equal to 0. And the sum of cos and sine over n. That's because they are phase shifted. So the multiplication of these 2 points here is 0. Multiplication of these 2 points are 0. These 2 points are 0. But this only holds true if our points are equidistant apart. Now, what about the term sine squared over n? And turns out that this is equal to cos squared over n. Now I want you to try and think about this and see how you could get the answer of a half. Alright, so we can use this to use a special case to reformulate our matrix into the following. So we can say, instead of, well, n stays n, sum of cos omega t is 0, sum of sine is 0, sum of cos is 0, sum of cos squared we said was a half, so this is n over 2. Sum of cos sine is 0, sum of sine is 0, cos sine is 0, sine squared is also a half, but because we have n data points, it's n over 2. Alright, so we rewrite our matrix. Sorry, this is B1. And that is equal to sum of y cos, sum of y sine. Alright, so in other words, A0 is equal to sum of y over n. A1 is equal to 2 over n multiplied by the sum of y cos of omega naught multiplied by t, and B1 is equal to 2 over n multiplied by the sum of y sine omega naught multiplied by t. Okay, now let's apply this in an example.